we will derive the relationship between the speed and the load torque in a different way. One way of deriving the relationship is, of course, is to write down the equations that relate the various quantities. Some of them we have already written down. We wrote down the equation for the electrical circuit: applied voltage EA equal to the back EMF, which is KB times omega m, plus RA IA, the armature drop. Then the torque equation, which is the torque produced by the motor, which is KT or KB into IA, equals the load torque TL plus KF times omega m, the second term being the frictional torque. This is under the assumption of steady state. The current, armature current, is not changing, so there is no inductor drop, and the motor speed is not changing, therefore there is no inertia term. So we just had these two equations, and we solved them earlier. We solved them to get omega m in terms of the remaining quantities except IA, and one could find another expression or an expression for the armature current separately. But of course we are interested mainly in the field current, in the motor speed rather than in the armature current. So we looked at only the equation relating omega m to the quantities such as the applied voltage EA, the load torque TL, and the various coefficients: armature resistance, coefficient of friction, and the back EMF or the torque constants. But now that we have decided to change the scheme by using feedback, the armature voltage is not directly applied, that is, it is not a voltage which is somehow going to be kept fixed and applied to the armature. We are going to produce it with the generator, and therefore that voltage in turn is controlled by the field current of the generator, which in turn will be controlled by the output of the difference device that we have looked at. So we can now write down a new equation relating the armature voltage EA to the output of the error device or the comparator, and therefore we call this coefficient Ka. So we have EA equal to Ka times E, and there is one more equation relating the output of the comparator to the reference input ER minus the tacho generator or the feedback voltage, so K tacho generator into omega m. So we have to now consider these two equations in addition to the earlier two equations, and then one can get an expression for omega m, the motor speed, the steady state motor speed, in terms of what? Not EA any longer, because EA is determined by small e, the error, so called error voltage, which in turn depends on the reference voltage and the motor speed. So finally we will have an expression for omega m in terms of the reference voltage ER, and in this expression what other terms will appear? The parameters of the drive will appear, that is, the armature resistance KB and KF, the coefficient of friction, will appear as before, but in addition we have two new coefficients. We have the gain, so called gain of the forward path Ka, which relates the armature voltage to the actuating signal E, and the feedback signal coefficient KTG, which relates the feedback signal to the output quantity omega m. So we will have two more coefficients, Ka and KTG, and what I asked you to do was to see the effect of changing this Ka on the value of omega m when the load torque changes. When the load torque is at the rated value, the motor will run at the rated speed, there will be no steady state error, that is right. Therefore the value of omega m will be the desired value of the motor speed. But when the load torque is not at the rated value, then the speed is going to change. The question was by how much, and in what way will this coefficient Ka affect the speed error, the steady state error in speed when a disturbance takes place. This disturbance that we are talking about is a change in the load torque. Of course the other coefficient also, K tacho generator, that is the coefficient which appears in the equation for the feedback signal, that also will affect the steady state error. Now, as I said, these are all steady state calculations, and this is not enough, because the conclusion that we will draw from this steady state analysis will be that the greater Ka is, the less will be the steady state error, and therefore one would be tempted to increase Ka to as large a value as may be practically possible, in the hope that the steady state error will be therefore reduced to a very, very small value. But I mentioned that this Ka has an effect on the transient error, and we have not looked at the transient performance so far, and that is something which has to be looked into, and we will do that. But before we do that, let us take a brief look at a technique which is useful when we look at some small system problem like the motor case that we are looking at, where there are not too many components, and the system, although it may have looked more complicated to you, especially when we have introduced feedback, the system is not really that complex. It really does not have too many subsystems or too many devices. Moreover, the relationships between the various signals or the various quantities are also fairly simple. For example, the armature voltage that is generated is simply proportional to the actuating signal E. So, there is a simple coefficient relating the two. Similarly, the back EMF is simply proportional to the speed, etc. So, the relationships between the various signals or physical quantities are also very simple. In this case, they are what are called algebraic, or it is almost arithmetical. Not only that, they are simply multiplication, addition, subtraction, and nothing more complicated than that. We do not have any sinusoidal function or exponential function or any square and things like that appearing in these expressions. Of course, no derivatives occur because we are looking at the steady state. Once we want to take into account what is actually going to happen during the transient period, we will have to take into account the derivative terms, and therefore the equations will not be such simple equations, but they will be differential equations. But even for such differential equations, some of the techniques that I am going to talk about are applicable. Now, this is a technique, or this is almost a formula, and that is what it is usually called, which was discovered by Mason in the 1950s, and this is therefore called Mason's gain formula. Now, Mason was looking at problems of the sort that I am talking about, but he was not looking at control systems only. He was thinking of systems which could be of other kinds. In particular, one could be looking at an electronic amplifier as a system under study, and especially when the system has feedback in it, that is, when there is some kind of that loop arrangement, one signal affects another, and that signal in turn affects the first one, and there is some kind of an intricate relationship between these various signals. So, Mason was looking at that problem, and he discovered this gain formula. Now, that was almost 50 years ago. The formula is really suitable for people, for you and me, to understand, to get some understanding of what can happen if we make some changes. So, it is a very useful tool for qualitative understanding of small systems. The formula, of course, can be used for large systems and will give exact quantitative relationship between the various signals. So, the formula is applicable in a very large number of cases where such relationships are simple enough, but today one would find it advantageous to use a computer program to do all these calculations, especially when we are looking at the situation in the transient state and not in the steady state only. And therefore, when we are going to look at differential equations, then today certainly it is possible to use not only write computer programs on your own, but use ready-made computer packages which enable you to handle the problem at hand. And therefore, Mason's gain formula is not necessarily to be used in such calculations, but for conceptual understanding, for getting some feel for what can happen if we do some changes, Mason's gain formula is a very good tool, and therefore we will take a little time to look at it. I will not prove anything, I will only state the result or the formula, and will not really go into the full generality of it. We will right now look at whatever is enough for our purpose at hand. The gain formula, as I told you earlier, arose out of Mason's study of signals, that is various physical quantities that are associated with a system which consists of a large number of interconnected subsystems. At that time already the idea of a block diagram was commonly being used, so that was not anything new. Engineers had started using block diagrams such as we have already used. And as I told you, the block diagram really enables us to concentrate on only a few signals associated with what is represented by that block. For example, when we represent the motor and the load by a block, perhaps the only relevant signals, as we saw, were the armature voltage, the speed, the load torque, and perhaps the armature current, if it might be of some interest or use. Other quantities we don't write explicitly. Also, with this block, ultimately we will simply associate an equation or two equations which express relationships between these signals. Now, the technique introduced by Mason goes a little further. One can look at the simplest case where you have only two variables or only two signals or only two quantities associated with some device or with a system. You can think of one of them as the input quantity and as the other as the output quantity, depending on what particular significance those quantities have. But if you are only interested in the relationship between these two quantities, then sometimes it does not matter which one is regarded as input and which one is regarded as output. If you do not mean by input and output literally that input is what you are going to change in order to make the output change in a certain way. So, in the simplest case, we will have a block or a system which has two variables or signals associated with it, with a very simple relationship between these two signals. And the simplest relationship that one can think of in our context is just what is called a linear relationship, or more specifically, one signal is simply a multiple of the other. For example, the amplifier block, or if you think of the so called error signal or actuating signal somehow affecting the field current, and that in turn then giving rise to a certain armature voltage. If you only look at these two signals, the error signal E and the armature voltage capital EA, then already I have represented that by means of a single block, a small block, single block Ka, showing E as the input and capital E as the output. So, I have not shown in this the motor that drives the generator, the field current of the generator, and maybe the armature current of the generator, and all that kind of thing. I have only shown two variables which are of importance here: the armature voltage produced by that arrangement and the error voltage which is fed to that arrangement to produce that armature voltage. And so, there is this simple block Ka sitting between E and Ea. Mason goes one step further and replaces this by the following. And this is done not only for a block like this, but is done for the various blocks to get something which is different from a block diagram, but as we will see and as you can see, it is going to be very closely related to the block diagram. So, it is a different way of sort of conveying the information in the block diagram, and the advantage of doing it this way will become obvious as we go on. So, instead of using that block with that Ka inside the block, E going in and Ea coming out, we can denote it by means of a single line. This line of course sometimes is called an arc, although it is not arc of a circle or anything, it is a line. The two ends of it, the endpoints of it are to be associated with signals, and on the line I am going to put an arrow, and along the line I am going to write down a number or a symbol like Ka. And so now if I complete this new diagram, this is what it will look like. This point or the two ends of the arc, those points are called nodes, because what we are going to draw almost looks like what is called a graph of an electrical circuit or an electrical network, and in that context one uses the terms like node and arc, or sometimes one uses the term branch. One talks about a branch of an electrical network, and the nodes are the points where the branches, a number of branches are connected together. They are the connection points or the junction points of the electric network. So, what we have right now is a single arc or a single branch with two nodes. One is labeled E, small e, the other is labeled capital Ea. There is an arrow on the branch, and alongside there is the symbol Ka. All this is supposed to represent the relation Ea equal to Ka into E. The block did the same thing in a different way, Ea equal to Ka into E on the block diagram. This new method, if one knows it and therefore understands what it means, gives exactly the same information, Ea equal to Ka into E, that you can have the block diagram, you can have this single branch, and you can have the equation. They all are ultimately related to one another. Now, if this was the only thing, then there is hardly any point in even drawing a block diagram or this kind of a graph with only one relationship and only two signals. One might as well write the equation itself. But of course, in a practical case, we just do not have one block. Already in our motor control example, we had a number of blocks, and therefore we will have a graph which will have not just one branch but a number of branches, and maybe not one node but or two nodes, but more than two nodes. Such a graph, because it represents really something that has to do with signals, was called by him a signal flow graph. The word flow is not to be taken literally. It is not that along that branch something is flowing from one end of the branch to the other. So, do not interpret it that way. The symbol Ka that is associated or put alongside the branch is not something that is flowing through that branch at all. Neither are the two labels that are associated with the nodes are flowing through that branch in any sense of the term. But in particular situations, for example, if you had a hydraulic network or if you had an electrical network, then as you know, in an electrical network we like to talk about charges flowing or even currents flowing, and the arrows very often represent the direction of flow of current or the reference direction of flow of current or positive charge. And so this word flow has been used, so let us use it. So we will call it a signal flow graph. So what we will do is, now for the block diagram of the motor, we will construct a signal flow graph, and then I will state Mason's gain formula then I'll apply it and we'll obtain the relationship between the motor speed and the other parameters and the reference voltage. So instead of writing equations and then manipulating them, substituting, solving, etc., we'll do it this way. As I said, this is, as you can see also, this is certainly really for human consumption. I have to draw a graph, then I will look at it, then I will do some operations or some mental operations on the graph, and then write down using that formula some expressions. So it's going to be useful only when the signal flow graph is not very large. When the graph is large, when the system is large, the relationships are more complicated, not any longer linear, then one will have to use computer programs or computer packages. Now these two nodes E and capital EA, there is an arrow. One of them, obviously E is going to be called the input node and the other node is going to be called the output node. The arrow points from the input to the output node. Now as I said earlier, these terms are not to be taken literally, that is, something is being put in at node E and something is coming out of node EA. It is not that which is communicated by this terminology of input and output. In fact, once I have that arrow there, I don't have to call E input and call EA output or something. I can simply say node E or quantity associated with that node, that is E, and quantity associated with the other node, that's EA. The relationship is EA equal to K into E. Now which way is it to be written? That is, I have written EA equal to KA into E. I have not written E equal to KA into capital EA. Now that is told by this arrow, and that's the only function of the arrow here. The arrow tells you that the signal at the what is called the head of the arrow, EA here, equal to this symbol KA, and this is called the transmission coefficient. Unfortunately, there is no transmission taking place, but as I said, there are analogies or other situations where there may be some transmission or flow taking place. We can simply call it the gain of the branch gain, but sometimes it is called the transmission coefficient or transmission, multiplied by the signal at what is called the tail of the arrow. The arrow has a head and the arrow has a tail. The signal associated with the node to which the arrow points, or on the head side of the arrow, equal to the transmission coefficient or transmittance or gain of the branch, multiplying the other signal, the signal at the tail end of the arrow, or the signal associated with the node at the tail end of the arrow. So this is the simplest block in the closed loop system that we are looking at. Armature voltage is just a gain times the error signal E. Now let's look at the other parts of the system, and simultaneously you can look at the block diagram and see what are the things that we are going to do. Now the block that represents the motor is a little complicated, although earlier we just showed one single block with EA as the input, omega m as the output, perhaps the load torque also as an input, and armature current as another output. And that was because there were two equations that we could write relating these various quantities, and it was enough to think of them together as one single block. But now, since we are going to use this idea of a signal flow graph, we will have to break it up into parts and then build up the graph from these simple parts. So for example, look at the armature circuit equation EA equal to the back EMF coefficient into omega m plus RA into IA. So it says that some signal armature voltage is a sum of two other signals, something which is called the back EMF, which cannot be really measured when the motor is in operation, and something called the armature drop, which also cannot be measured separately when the motor is in operation. So EA is a sum of these two signals. Now, we did not represent this in the block diagram at all because the block just stood for the whole thing, motor and load. But now, if we want to represent this relationship between these signals, then how shall we do it? Mason's idea was that one signal is a sum of two signals. So, devise some means whereby this information can be put down graphically. Some signal is a sum of two other signals. Now, this he did by simply using the following convention. I am going to write down, I am going to put down three nodes. One of them I am going to label KB omega m. The one more I am going to label as RAIA, and the third node I am going to label as EA. Notice that the nodes are not labeled as 1, 2, 3 or ABC or whatever. The nodes are labeled directly with the name of the signal. So, immediately from the diagram or from the signal flow graph, we can see that this is armature voltage, this is back EMF, this is armature current. So, one can see the signals immediately. There is no need to write down, number the nodes as 1, 2, 3 and branches as A, B, C, D, or when you use some network solver program or network analysis program, you have to label all the components and devices and so on and so forth. There is no need to do that here. So, I have these three signals EA, KB omega m and RAIA, and I want to show this relationship that EA is a sum of these two. Mason chose this following simple idea: just draw an arrow from KB omega m to EA and another arrow from RAIA to EA. Now, what does this say? Well, suppose that RAIA thing was missing, that branch was not there, then you would have simply EA equal to KB omega m. On the other hand, suppose the KB omega m term was missing, that is, that branch was missing, then you will have only EA equal to RAIA. But now we have both of them present. So, simply interpret EA as the sum of these two. So, at the node, when there are incoming arrows, you have to assume that a summing action takes place, a sum is formed, and one can describe it by saying that the signal associated with the node is the sum of all incoming signals. In our case, EA equal to KB omega m plus RAIA. Is that quite correct? Not really, because on these two edges, along with these two arrows, I have not indicated their transmittances or gains. So, if I want to be really quite correct about it, I will have to put down 1 and 1 alongside each of these branches. So, the node KB omega m is connected to EA through a branch with gain 1, the other node is connected also to EA with gain 1, the arrows are as shown. Therefore, EA is the sum of the signals which are associated with those two branches whose arrows point towards EA, multiplied by the gains, in this case 1 and 1 each. So, in this way one talks about incoming signals. For EA, KB omega m and RAIA are the incoming signals, and this node not only stands for EA, but it also stands for this equation EA equal to KB omega m plus RAIA. That is, it also stands for the operation of summation or summing, of adding. This is a nice and simple way of representing therefore addition on a diagram. It is a convention, and therefore if you understand it and if you remember it, then only you can use it. But that is a part of life. If you want to go ahead, there are some things which you have to understand, which you have to remember, and then you find that they are useful. I can make a slight change in the flow graph. I can keep the node EA as it is, but now the other two nodes, I will label them as omega m and IA, the motor speed and the armature current, because I am not really interested in the back EMF, I am interested in the speed. Similarly, I am not interested in the armature drop, I am interested in the armature current. So, how do I draw the graph now? Well, from omega m to EA, draw an arrow, and the gain of this branch will be simply KB. Similarly, from IA to EA, draw an arrow, and the gain of this branch will be RA. So I have 3 nodes now, 3 signals, EA, omega m, IA, and I have 2 gains of 2 branches. I have 2 branches, one with gain KB, the other with gain RA, and all this represents that simple equation EA equal to KB omega m plus RA IA. So that takes care of one of the relationships that we have used earlier. Now let us look at the second relationship, which is the mechanical relationship between the various torques. This equation was what KT into IA was the torque produced by the motor equals TL, the load torque, plus Kf into omega m. Omega m being the speed of the motor, this is the frictional term. Now I would like to represent this equation in the flow graph manner. So how shall I do it? Well, if we go by what we did earlier with the armature equation, maybe I should take KTIA as one node, that is one signal, and that is equal to TL, so show that as coming in, and Kf omega m as the other signal that is coming in. And certainly that is possible, it is possible to do it that way. So I will show it. KTIA is the node to which these 2 signals are going, TL with a gain of 1 and omega m with a gain of Kf. Nothing wrong with this. This stands for the equation KTIA equal to 1 times TL, that is just TL plus Kf times omega m, which is exactly the equation that we had. Notice that TL and omega m appear as some kind of input signals in this signal flow graph, and IA appears, or KTIA appears as an output signal. Now as I said earlier, the load torque, is it an input quantity or is it an output quantity? It is certainly an output quantity in a practical sense. The purpose of the motor is to produce load torque. The output of the motor is the torque or motor torque, if not the load torque. That is the output of the motor. So I am showing here TL as an input, but as I said, these words input and output do not have to be taken literally. For us, when you have a line with an arrow, then one signal is called the input and the other is called the output, and all that matters is the relationship between the 2 signals, and the arrow tells us which way the relationship is to be written. That is about all. But I can go a little step further, and instead of writing KTIA, because KTIA is the torque produced by the motor, but again I am not interested in the torque produced by the motor as such, and so I could get rid of that coefficient KT by dividing that equation by KT. So in other words, I take the equation as IA, the armature current, is equal to TL divided by KT plus Kf omega m divided by KT, and therefore I can draw a graph where IA is the output node. There are 2 input nodes, load torque and omega m, these are the 2 input nodes, and with the corresponding gains, the gain from the load torque is 1 divided by KT, and the gain from the speed of the motor is Kf divided by KT. So this represents now the second equation, and now I can combine these 2 separate parts that I wrote or drew earlier. There was this equation for the armature voltage, and there was this equation for the armature current, and I can combine them. I can combine them by simply superposing, except there is one condition that has to be observed, or one restriction that has to be followed, and this is one of the, if you feel it is a limitation of the signal flow graph, because each node will not only denote a voltage or a current or a signal in general, each node will represent or denote or stand for a signal, but because a node may have more than one incoming arrow, each node also stands for a sum or a summation. Therefore, each node can only represent one equation. Each node can represent only one summation equation. So, you cannot have two equations, let us say showing EA as a sum of two signals and another equation showing EA also as a sum of two other signals, because then the same node will be doing this double job. And if I have a node with not two but four incoming arrows, then by this convention EA is the sum of all those four incoming signals and not E equal to sum of two incoming signals on the one hand and also E equal to sum of two incoming signals on the other hand. So, because of this dual use of the node, node denotes a signal and node can also denote a summation or represent the operation of summation. This is something we have to take care of. So, with this in mind, now can I combine the two signal flow graphs that I drew earlier, the graph for the load torque omega m as input nodes and in turn they determining IA is the output node, and omega m IA as the input nodes and they in turn determining EA as the output node. Is there going to be any problem in superposing these two diagrams? Well, there is none, although we will see that that is not going to be that useful and we will therefore change the diagram. But one should know the reason for making these changes. It is not simply that the book draws the diagram in a particular way and therefore all you have to do is copy it in that way. You should understand why diagrams are drawn in a particular way and why not in some other way. So, let us combine the two diagrams. So, I have TL as one node, omega m as another node, IA is the armature current and there is that equation. I am putting down the gains 1 by kT here and kF by kT there. So, that is one equation. IA output node signal is the sum of two input nodes multiplied by their transmittances, that is the torque equation. Then this IA in turn is an input node affecting EA through a transmittance RA, and there is omega m also, and therefore I will draw another arrow from omega m to EA with a transmittance of KB. So, I will have now a diagram in which there are two nodes TL and omega m from which there are only outgoing arrows. There is no incoming arrow for these two nodes, and usually such nodes only are called input nodes of the whole graph. If I talk about the whole graph that I have now and it has 1, 2, 3, 4 nodes and 4 variables, then TL and omega m are said to be input nodes because there are no incoming arrows, there are only outgoing arrows. Whereas EA is said to be an output node because there are only incoming arrows and no outgoing arrows, and IA is then said to be what? An intermediate node because it has arrows coming in and it has arrows going out. What is the difference between these three? At an input node like TL and omega m, there is no equation. There is only a signal associated with the node and nothing else. At other nodes, both the intermediate nodes and the output node, there is an equation. The output node, because it has incoming arrows only, therefore it stands for an equation. The intermediate node also, because it has incoming arrows, it also stands for an equation. So, at each of the intermediate and output nodes corresponding to each one of them, we have an equation, whereas for an input node there is no equation. So, that is what distinguishes the input nodes from the output and the intermediate nodes. And from the diagram or from the graph, the way of finding out which are the input and output and intermediate nodes is by looking at the arrows. Now, strictly speaking, the distinction between the intermediate nodes and the output nodes is not that important, because as we will see, the gain formula which Mason introduced applies for both these intermediate nodes as well as output nodes. In fact, that is a good point about it. So one need not worry about this distinction between intermediate nodes and output nodes, but what is an input node must be understood very correctly. It's a node from which there are only outgoing arrows, no incoming arrows. So in this diagram or graph, TL and omega m are the input nodes and the other nodes are not input nodes. Now, given a graph like this, one can apply what is called the gain formula, Mason's gain formula. This, of course, if you remember, is the speed control of the motor without using feedback. So EA, the armature voltage, is going to be kept constant and we will let the motor run no matter what happens to the load torque or parameter changes and what not, and therefore omega m is not going to remain the same. Now, because omega m for us is the output quantity, that is, we are really interested in finding out how omega m is affected by these other things. Therefore, the way we wrote down the equations and the way we represented them on the signal flow graph is not so helpful. For example, the load torque TL appears as an input node, and that's okay, because in a way that's can be thought of as a disturbance input. Change in TL is essentially a disturbance, but omega m is not an input variable. It's not physically an input variable of the drive. In fact, EA is the physical input variable to the drive, and so we have sort of turned upside down the input and output quantities. EA should be the input, that's now appearing as not an input but as an output node. Omega m is the output, that is appearing as an input node. IA is an intermediate quantity, yes, because IA is neither an input nor is it an output quantity. It is not of directly of interest to us. The load torque TL, however, appears correctly as an input, although from practical point of view it is the output of the drive, or it is what the drive produces. But when looked upon from the point of view of disturbance, changes in TL are disturbances which can act like inputs, unwanted inputs, unknown inputs to the system. So having TL as an input node is okay, but this thing having EA as output and omega m as input is not quite satisfactory. And therefore one can try to change the diagram or the signal flow graph as we will, but let me repeat, the graph as we have drawn is quite correct. There is nothing wrong with it. The graph, because there are two nodes which are not input nodes and therefore which have incoming arrows, the signal flow graph represents two equations. And what are those two equations? Look at the node EA, it has two incoming arrows, therefore EA equal to the sum of the incoming signals. Now one of the arrows at the tail of it is IA, so IA into transmittance RA, that is one term in the sum. The other arrow has at its tail omega m, so omega m into KB is the signal that is coming along the other path, as it were, and therefore EA equal to KB into omega m plus RA into IA. So this node not only represents the voltage EA, but it also represents an equation. And that's the equation that we had written earlier. Nothing wrong about it, therefore, as far as the diagram or graph is concerned. What about the second node IA, which is also not an input node? Well, remember, when you are thinking of an equation associated with a node, you are only to look at the incoming arrows. So that there is an arrow going out from IA is not to be thought of when writing down the equation. In fact, that's what makes it an intermediate node. There are incoming arrows as well as outgoing arrows. Now, what is the equation associated with this node IA? Look at the graph. What are the arrows which are incoming? What are the signals at the tails of these arrows? What are the transmittances or gains of these two branches which are pointing towards the node IA. One of them is from TL multiplied by 1 by KT, the other is from omega m multiplied by Kf by Kt. And so at the node IA, we not only have the signal IA associated with it, the armature current, but we also have an equation IA equals TL into 1 by Kt plus Kf by Kt into omega m. And this is almost the equation that we wrote, except we have divided both sides by Kt. So instead of Kt IA equal to something, I have IA equal to a sum of two terms. So as far as this signal flow graph is concerned, it represents the two equations for the steady state operation of the simple DC motor drive. You will not find this diagram perhaps in your textbook, simply because, as I said, here omega m appears as an input quantity and EA appears as an output quantity, whereas I may wish to see them in their opposite roles, EA as input and omega as an output. But the signal flow graph is quite correct. It represents the two equations 100% correctly. There is nothing wrong with the signal flow graph. But can we make some changes or draw another graph in which EA may appear as the input quantity and omega m may appear as the output quantity? And this is what I want you to remember and realize, that if I have an equation, I can represent it on the signal flow graph in one particular way, but I can represent it in a different way also. And there is nothing wrong about doing it. The only thing that you have to remember is that at each node there is only one equation. So you can't have a node variable equal to some particular summation and also equal to some other summation and represent this on the diagram or on the graph by all arrows coming in, because then by convention that signal will be the sum of all incoming arrows. So that is the only restriction in drawing signal flow graphs, and therefore when drawing signal flow graphs one has to take care of this fact, that at each node we will have only one equation. Nowhere should it happen that you are trying to represent two equations by a single node. Alright, so let us look at the armature voltage equation, EA equal to KB into omega m plus RA into IA. How can I rewrite this equation and then draw the corresponding branch of a signal flow graph? The way it was, we just took omega m IA as the incoming nodes, EA as the output node, and therefore drew that branch, two branches going from omega m and IA through transmittances KB and RA to the node EA. But now if I decide that I would like EA to appear as far as possible as an input node, because physically when I want to think about the drive, I want to think about the armature voltage as an input variable. If I want to do that, then I would like to see EA as an input node, and therefore that will not be the node with which the equation will be associated. Then which other two signals? Now we have a choice, we have omega m and we have IA. We have speed and armature current. Which one of them shall we choose therefore as the output node or the node with which we will associate the equation? And therefore one of the two, omega m and IA, will then become an input node. Now as you can see, there are two choices possible, and so it can be done in either way. At this point we may not know which one is going to be more useful of the two. So one way will be, of course, therefore we start doing it, start with EA as an input node, omega m as another input node, and therefore IA will be my node which corresponds to this summation, and therefore what will be the transmittances? Going for EA to IA, what will be the transmittance? What I have to do is take this equation solve it for IA in terms of EA and omega m, and then draw or show the gains or the transmittances on the signal flow graph. So you can see that for IA, the transmittance coming from EA will be 1 by RA. Why? Because if I take this equation and I do try to solve it for IA, let us say by taking IA to one side, so that I get RA IA equal to EA minus KB omega m, and now I solve it for IA in the sense I express IA in terms of the other two. So I will get IA equal to 1 by RA into EA minus KB by RA into omega m. The gain or transmittance from EA to IA is plus 1 by RA. So it's good to do it slowly rather than look at that equation and then try to draw the signal flow graph directly. The other coefficient, however, has a negative sign. It is minus KB divided by RA. So that armature circuit equation I can represent by this signal flow graph, in which EA and omega m are the two input nodes and there is a single output node IA, and this stands therefore for that single equation IA. We can do it choosing omega m as the output node and EA and IA as the input nodes. Why don't you try it? What is to be done? I have to solve for omega m in terms of EA and IA. So transfer some other term to the other side and get an expression for omega m as some coefficient into EA, that will be the transmittance of that branch, plus some other coefficient into IA, that will be the transmittance of the other branch. So I could also have a signal flow graph with EA and IA as the input nodes, omega m as the output node, and with two transmittances appropriately chosen. So for example, from that equation, the transmittance from EA to omega m is KB, and the transmittance from IA to omega m once again has a negative sign, and it is minus RA divided by KB. Now let me emphasize once again that both of these are correct ways of representing that equation, as was the third way of representing the equation, namely EA as the output node, omega m and IA as the two input nodes. So all the three ways are equally correct. Let nobody tell you that this is not right and that is right. Of course, what is more useful, what is not so useful, that will depend on what happens as we proceed further. But at this point, what is important to note is that an equation can be represented on a signal flow graph in this particular way. An equation expressing one variable, one signal, as a summation, and by summation one means plus sign, all right, but a coefficient which may be negative, of a number of other signals multiplied by their transmittances. And so from those nodes draw arrows pointing towards this signal, which is the sum, show the transmittances along the various branches. This is the way of representing that equation on or by what is called a signal flow graph, and there can be more than one way of doing this, and it's only experience, or what it means is that you try this, try that, then eventually you see that this is better than that, and then you can say to yourself, why did I not think of it earlier, and so on. But that's not the point of it. One should know that there are alternatives, they are all equally correct, and of course one should learn that this works better than that, and so on. Now as homework, I would like you to look at the torque equation and then write it in two different ways. We wrote it for IA in terms of the other two quantities. Now you can write it for each one of the other quantities in terms of the remaining two quantities and draw the corresponding signal flow graph. Okay. So for example, TL as the output node, armature current as an input node, omega m as another input node. That's a graph that can be drawn. And this next second one, or really the third one, will be omega m as the output node, IA as the input node, TL as the input node. So for that second equation also we will have a choice of 3 graphs. For the first equation we have a choice of 3 graphs. But now we don't want these 2 graphs to remain separate. Why? Because there are some common signals. In fact, almost all the signals are appearing there. Omega m, our crucial signal, is appearing in both the graphs. The armature current also appears in both the graphs, although it is not of direct importance or use to us. The other signals, EA, appears in only one graph, TL appears in only one graph. So of the 4 signals, omega m, IA, TL and EA, omega m and IA appear in both the graphs, one corresponding to the electrical equation and the other corresponding to the mechanical equation. Whereas the armature voltage appears only in the electrical equation, the load torque appears only in the mechanical equation. And that is quite natural, because the armature current, because it is flowing through an armature which has a resistance, makes that contribution RAIA in the armature circuit. But on the other hand, this armature current, because it is flowing in the presence of a magnetic field, produces a torque. Therefore, it appears in the torque equation. What about the speed of the motor, omega m? Why does it appear in both the cases, both the equations? It appears in the mechanical equation because of friction. There is a shaft rotating, maybe there is a fan mounted on the shaft, so there is friction in the bearings, there is this windage, air is to be moved, therefore there is a torque required for that, which is proportional to omega m. So omega m occurs in the mechanical equation. And why does omega m occur in the electrical equation? This is because we have conductors which are moving in a magnetic field, and therefore, going back to Faraday, an EMF is produced in that conductor, and therefore omega m appears in the electrical equation as well. Now our problem is of combining these 2 signal flow graphs, one corresponding to the electrical equation, the other corresponding to the mechanical equation. I want to combine them in a single graph, but when doing this I want to take care of this fact that I mentioned earlier, that is, a node of the graph should be associated with at most one equation. There can be a node which is not associated with any equation. What is such a node called? It is called an input node. An input node is a node for which there is no equation. There is only a signal associated with that node, no equation. So there will be some input nodes in the final diagram with which there may be no equation associated, but with any particular node there should be at most one equation and not 2 equations or more than one. So combine these 2 signal flow graphs so that this condition is satisfied. Find out whether there is only one way of combining these 2 graphs, that is, actually we have a choice of 3 graphs for the electrical equation, 3 graphs for the mechanical equation, and so I could think of 9 combinations. Which one of them will fulfill this condition, that when I put the 2 graphs together, literally I superpose them, I will not find that one node is doing the job of 2 nodes, that is, one node stands for one equation and it also stands for another equation, because when you combine them, a given node stands only for one equation, because you can only see incoming arrows even if there are outgoing arrows. The node associate, the signal associated with that node is the sum of the incoming signals, that is, the signals associated with those nodes multiplied by their transmittances added up. This is the way we have chosen, or Mason suggested that we represent equations, and so once you make that convention, you have to stick to it. It is a logical requirement, because how do I distinguish between one node representing only one equation and one node representing two equations? Although there are some tricks that one can play, and therefore one can do some of these things which are not obvious at first glance. For example, I can always put a what may be called a useless branch like this one, which has a transmittance 1, and it has only at both of its nodes whatever signals are associated with them. If whatever are the signals coming in at the other end, it does not matter what they are, if that signal associated with that node is x and the other signal is y, and whatever branches go out, it does not matter. So if you have a very simple situation like this, a branch between two nodes x and y with a transmittance 1, and y has only one incoming branch, and x of course could have more than one incoming or outgoing branches, that does not matter, then what is the equation that corresponds to this node y? It is simply y equal to x. It is simply y equal to x. That's is there any point in writing down that equation, or therefore putting that branch with transmittance 1? There is really not much point, except this condition that we are insisting upon. If that is to be satisfied, something like this can be used or may be required. So do this homework, and we will then look at what we can do with the composite signal flow graph. We will look at the statement of Mason's gain formula, apply it to that composite graph, and get a nice formula rather easily by looking at the graph and applying the gain formula. Because when I say easily, it means after you have understood and remembered Mason's gain formula correctly, and you can apply it to the particular signal flow graph correctly, and of course after you have drawn the signal flow graphs correctly. So it is only when you can draw a graph correctly, first of all therefore you must write down correct equations to start with, then represent them correctly by the signal flow graph, then you must remember what the Mason's gain formula is, and then you must apply it correctly. If you do all this, then hopefully you will not go wrong, and you would have found out the desired equation or relations that we are looking for.